Welcome to Precalculus Concept 17a. We're going to solve a polynomial inequality, and there's 4 boxes. So here is the first idea. We want to first understand what a polynomial inequality even is. So a polynomial inequality is any sort of inequality that can be written in the following sense. Take any polynomial and then put an inequality in it, less than or equal to, greater than or equal to, and they're all set to 0. All right, they're all set to 0. So a polynomial inequality is any inequality that looks like this form. Here are 3 real simple examples for you. 3x squared plus 2x plus 5 is greater than 0. That is a polynomial inequality. X squared plus 5x plus 4 less than or equal to 0. That is a polynomial inequality. And here's another one. X squared minus 7x minus 10 is greater than 0. That's another polynomial inequality. So it's any polynomial that you have, just written with an inequality on the back end and then set to 0. Okay, now that we know what a polynomial inequality is, we can talk about what a polynomial inequality means. Okay, so let's do this real basic example. I have x squared minus 7x plus 10, and I've set it greater than 0. Another way of asking the same question that I really want you guys to understand is what values of x make the statement true? Make the statement true. Make the statement true. Okay, so it means like if I were to plug in a value of 0 for x, like as an example, if x was equal to 0, I would get 0 squared, I get 0 minus 0, 10 greater than 0. Is 10 bigger than 0? The answer is yes, so x equals 0 is a solution. The question is, how do I talk about all of the solutions of the inequality? Okay? So one strategy that we're going to do is we're going to look to the graph. So if I were to take this and I were to graph it over here, which I've done for you, I would get a parabola. And you would notice that the intercepts are at 2 and at 5. And you'll also notice that there is a part of a graph that is above the x-axis, and then there is a part of the graph that is below the x-axis. See? So all of these parts up here, this part of the graph here and this part of the graph here, those are all above the x-axis, meaning that they are greater than 0. All of the other parts, such as this part down here and down here and down here, those are all below the x-axis. That means that those values are less than 0. Okay? So the graph gives us a pretty good idea of where the answers are. So the answers for this thing are, what values of x make this a true statement? Well, the values of x that make this true are all of these values of x and all of those values of x. So how would we say those two things? That's what we're trying to figure out. That's what it means to be bigger than 0. All the ones in the middle, like all the ones right here, give us a negative output, which is below the x-axis. So those are not the ones that we would want. So this is what a polynomial inequality means. We are looking for values of x that make the statement true. Okay, box number 3 is an example of how you go about solving a polynomial inequality. I have 2x squared plus x is greater than 15. The first thing I want to do is get it into the form that I can use. So 2x squared plus x minus 15 is now greater than 0. Now it's in the form that I can use. I'm going to go ahead and factor this polynomial inequality into 2x and an x, and probably a 5 and a 3. I'm thinking a 5 and a 3, yes. And it would be negative 5 and a positive 3. Okay, so I have 2x minus 5 times x plus 3 is now greater than 0. I have factored the quadratic. Then I'm going to go ahead and pretend and set this equal to 0 to find what are called critical points. So if I set 2x minus 5 times an x plus 3, and I set it actually equal to 0, what I can do is find critical points. So therefore, 2x minus 5 is 0. That tells me that x is 5 halves. Or x plus 3 is 0. That tells me that x is equal to negative 3. All right? So right there, basically, those are my x-intercepts. Those are where the parabola would then touch the graph. This shouldn't be anything new. But what we do with this information is probably a new procedure for many of you. So what we're going to do is we are going to draw a number line, and this is going to represent the x-axis. And on that number line, I always have to put the number 0, just so I give myself a reference point. And then I'm going to put my critical values of negative 3. So here's negative 3, and I'm going to draw a dashed vertical line at negative 3. I'm also going to put a line at 5 halves, which is 2.5. So 1, 2, and then a half right there. So this is what it sounds like if you're going to do that, if you're in Miss May's class. So here is 5 halves, all right? So now what I have here is I have 3 different regions. I have this region to the left of this critical point. I have this region sort of in the middle of these 2 critical points, right here, this blue region. And then I have this region over to the right of the other critical point, or my intercept, at 5 halves. So I have a yellow, a blue, and a green region. What we're going to do is we're going to take a test point for each region and determine whether or not it makes this statement true. That's what we're going to do. So I'm going to do this in red for you. So any point in this interval over here, such as negative 4, for example, I'm going to test the point negative 4. So here's what I'm going to do. I'm going to take 2, negative 4, and square it, plus negative 4 minus 15, and I want to see what value I get. If I do all of this, I get a value of 13 when I evaluate. 13 is a positive number. That means it's above the x-axis. That means it's over here in this region. Okay, if I take 0, 0 is a really easy test point. So if you can use it, go ahead and use it. So if I plug 0 in, I would get 2 times 0 squared plus 0 minus 15. Is that bigger than 0? Is negative 15 greater than 0? No, that's a false statement. Or I'd get a negative number. So I get a number that's down here. It's negative. Okay? And then if I pick a test point in this region, such as any one of these, so this is 0, 1, 2, like I could take the number 3, for example. I could test the number 3. And I plug it in, I would get a value of positive 6. So it would be over here. So if I took the number 3 and plugged it in, I get a value of 6. I'm just saving you guys the algebra here. Okay, so now we know what values of x make this a true statement. So what values of x are going to make that a true statement? Any value that is from negative infinity all the way up to negative 3, but we don't include the 3, and the union of this interval over here, 5 halves, all the way to positive infinity. So this is how we would represent the answer. There's no reason why this is spaced out in particular. It has nothing to do with the way I drew the graph. I just spaced it out. So negative infinity to negative 3 and 5 halves to positive infinity. That's the procedure that we're looking for to solve a polynomial inequality. Okay, here is your chance to shine. Go ahead and try and solve this polynomial inequality. Look back at box 3 for help. Hopefully got the right answer of negative infinity to negative 4 union 5 to infinity. Here's how I did it. The first thing I did was I got it into a usable form. Then I factored it. Then I found my critical points of 5 and negative 4. I drew a number line. I have my critical points at 5 and negative 4. I then took test points from each region. Negative 5 from the yellow region, 0 from the blue region, and 6 from the green region. I then plugged in and got a positive answer, a negative answer, and a positive answer. And that told me exactly where all of these are going to be positive or greater than 0. So therefore, it's any x that's between negative infinity and negative 4, or any x that is 5 or greater.